What is up, everyone? Welcome back to our data structure series in Golang. Last time we did linked lists. We started with singly linked lists and we did doubly. And then now we're moving on to slightly more complex data structures which we can create using these linked lists uh, that we've implemented. So this would be linear data structures, something like stacks, queues. So we'll be starting with stacks in this video. So I'm just gonna call this stack queue, and I'm just gonna do stack.go. Package stack queue. We can create. Okay, so now we need to think about this. Uh, so there's two ways of creating a stack. There would be one which is built upon a vector. Uh, so it would be a contiguous uh, block of memory which we are allocating for each item in our stack. So every time we push an item onto the stack, we allocate a contiguous uh, bit of memory with the whole stack. So it would be one block of contiguous memory. So basically, what that means is all of the memory would be allocated side by side. It would be something like this. If you looked at the memory, it would all be like one after the other. Of course, it wouldn't be exactly this way, but it's just a representation. And there's another method of implementing it, which would use linked lists. And in this case, the whole linked list is like it's all over the memory. We don't know where each node would be. All we have as a reference is the next pointer in each node, or the previous pointer in the case of using doubly linked lists. So that's the only way we know where another block of memory would lie, which would be a part of the linked list or the stack in our case. So that's the only way of keeping track of the whole linked list. So we can implement both of these types of stacks in this video. So let's just start with the one that's simpler, which uses the a vector to like we would use a vector to build our stack on top. So in order to differentiate both of these, uh, I'm going to call this stack uh, stack vector, and then I'll create another stack link, which would use one of the linked lists that we implemented. But now we're going to start with a vector stack. So let's think about this. We will need a stack, which would be a vector of int. So this would be our stack. This is all we need, honestly. And now we can implement our method. So for the purpose of the demonstration, I'm going to implement a push, a pop, and uh, and a peek method. So let's start with the push. We will need a value which should be an integer, and we need to implement that. There would be a pop, and there would be a peek. And the difference between these, if you're not familiar with stacks, is that push would push onto the stack. So this works exactly how a stack in real life works, where we insert from one end of the stack. Let's say that this is our stack, or for a better demonstration, I think it would be something like this. So this is how we push onto the stack, and the same way we would pop from the stack. So this is the only way we can insert and delete elements from the stack. There's no other way for the elements to move out of. And let's say if we wanted to insert a new item, we would call that pushing an item onto the stack, and that's what it would look like. And this is what popping would look like. And peek is just when we look at the top of the stack, whatever we have there, and we just return it back without popping it from the stack. So we're just returning the value of it. So we don't really need to keep track of the top of our stack in this case when we are using vectors, because we can simply do something like s dot value, but instead we'll need to pass references to modify the instance of the stack. So this is what we would do to append a value onto the stack. So it would push a new value to the stack. And if we don't use pointers here, it wouldn't like modify the underlying slice, the stack slice. The stack is basically it's a slice of ints. And if we want to modify this, we'll need to pass the references to them and update the reference of and use the reference to update our stack instance. So that's how that would work. So let's implement a test stack vector function where we will create a new stack instance and we will do make here, and then we can do stack.push. Let's push 1, 2, 3, 4, and then we can format print stack, and let's see what we get. And we'll need to pass the length of the stack that we want to initialize. We want to initialize an empty stack, so that's what we'll do. So let's just do a go run dot. Yeah, we need to call this from our main function. So stack use dot test stack vector, and now okay, so now we are able to push onto the stack, which is it should be working because we are just using our standard append method, but still it's good for understanding. So as you see, we have pushed onto the stack. We are pushing it at the end, and similarly we can push another value, and it would get pushed from this side. Now we also want to get like pop from the same side. So what we can do is we need to implement the pop method in a similar way. So we can keep track of the popped element, or we can just call it pop, and we get the stack, we get the length of the stack -1. So this is the popped element. Usually what pop methods do is it gets rid of the last element and it also returns the last element back. So now we assign uh, the stack to itself after we pop it, and we need to do something like this to use array indexing along with the reference pointers, and then we return pop, and we need to have that in our definition. Awesome. So we can we can do the same thing right here as well. When we peak, uh, we just return peak. So whatever the peak item was, that's what we are returning. Now we can test that out as well. We can try to peak and then we print. And in the case of peaking, we don't need anything. In the case of popping, we don't need any arguments. And we can try to get the peak here. We can print that out as well if we are getting the peaked item. Makes sense? Uh, so we have gotten the top of our stack and we haven't popped it either. Now we can try to pop from our stack. and we need to call the pop function, and now we can see that the item did get popped, and we can repeat this till the stack becomes empty. Awesome. So let's try to get an edge case here. What if we try to pop uh, from an empty stack? And we see that we are panicking, so we'll need to handle that case in our pop function, where we can check if length of s is equal to 0, then we can return, and we need to print something. So we can print something like stack underflow, and we can return nil here, or we can return like a -1. Yeah, that makes sense. Stack underflow makes sense. And now, since we're doing a stack underflow, we can also do a stack overflow, which would happen when the stack, the limit of the stack has breached, and we can't push any more items. So to do that, we will need to, instead of just having a slice for our stack, we can create a struct type. So our this would be our stack. You can comment this out real quick. There would be a data which would be an an integer array, and we would have a max size which would just be an int, and we'll need to update all of our operation methods. So we can do something like this where we set the data to append s.data with a value, and so now we're appending onto our data which we're keeping track of within the stack. Now we'll need to check before we append whether the data, the max size has been reached. So to do that, we will get the data length. We will see if it is s dot max size. If it is, then we just format dot println stack overflow, and we just return -1. Oh, we're not returning anything from the push, so we're we're good there. Uh, and we can do the same thing here where we just check the size of the data. If it is 0, then we just print underflow, or else we just pop from our data s dot data, s dot data. And the reason why we're getting rid of the pointer that we had earlier is because earlier our stack was just uh, a slice, just a slice, but now it is a struct of slice. It is a struct where we have data as the int slice, and we have a max size we're keeping track of, which is an int, and we can directly access this data without having to use the pointer. The pointer was only used because we wanted to access this underlying int slice, but now we don't need to have that. Awesome. So our pop method is covered. We can also check for the length of s.data. Uh, and if it is 0, in the case of peak, then we do the same thing, uh, where we return -1, and we just say that the stack is empty or stack underflow. That's what it means. We'll need to modify this. So yeah, the make function can only be used with slices, maps, or channels, but we cannot make a struct. We'll need to make it on our own. So let's just do that real quick. We'll just create an empty struct where the data is make of that with a initial size of 0, and the max size would be 0. Or I'm sorry, the max size we need to set that. So we can set it at 4. Let's try to push. more than four items onto the stack, and we can have the same values, but just for a better understanding, I'll just change them around real quick. Now try to push them, run the program. Awesome. Now we see that we're printing everything, which is okay, but you can just print the data. So I'm just gonna multi-select this, insert mode, and then add our data there. Cool. So now we can clearly visualize how our stack is working. Uh, as soon as we hit four elements, we are saying that the stack is overflown. But we see that another element is added here, which is problematic. Let's see why that's happening. Oh yeah, we need to return from here with, we'll just need to have a return there, or else we'll keep appending, and even when the stack is overflown, we'll just keep appending. So we need to stop that right there and return. So cool. Now, whenever we overflow, we're not pushing anything. So this is cool. And also we can try to pop once more to see that we are reaching the stack underflow at the end there. Awesome. So now our vector stack is working. Now we can move on to our linked list stack. So this should also be pretty simple since we've implemented our singly linked list in our previous video. If you've not watched that video, I'll leave a link to it in the description. So basically, we have a value and a next in each node, and the linked list would be would if we would keep track of the head node and the length of the linked list. Basically, since there is a head node, we would have a next pointer in that node, and we would create a chain of nodes in our linked list. So we'll need to create a type stack, which should be a struct, and yeah, we need to create a stack link because we've already created a stack here, which is also a problem. I'll rename this to stack vec. So we need to import our linked list here. To do that, we will import our repository, and we will do project, and we'll do a linked list here, which would be our new data. And we would have a max length from earlier, which would be an integer. We'll need our functions from earlier, so I'm just going to copy over them real quick. And we need to rename these functions as well. Push will be a push vec, and we have a test stack vector. Let's just copy over all of these functions, and we can get rid of this old stack now. All right, so we can now, wherever we have a vec, we can replace it with a linked. We can keep our functions, but we need to modify all of it, all of the bodies of these functions. So everywhere where we need uh, a return type, we'll just return 0, and we'll update our functions. So let's think about pushing to the linked list. So now that we have linked lists, it should be pretty simple because the way we've set up our linked lists is that we have an insert start and a delete start method here. And we can use these to our advantage and implement our linked list. So our stack, I mean. So we can simply just do s.data.insert start and pass our value. And that's all we need to do. Like we can also check like if s dot data dot, oh yeah, we are also keeping track of the length of our linked list. If I take a look at it real quick, we do have a length here, but we need to make this capital if we want to access it. We need to update it to a capital L to make it a public struct attribute. So all the places where we were using lengths, I've updated them to have this name now. And now we can use this to check if our linked list has reached the max length. If it has, then we just return, and we also print that the stack overflow. Yeah, and we can do a similar thing with pop. And now you see the advantage of how we've implemented our linked list. It does, uh, it makes it a lot easier for us to work with the linked list and create more complex data structures on top of it easily. So anyway, let's try to implement the pop now. So we can delete from the start again because uh, we only delete from one end of the stack. But now let's think about uh, how we can return the value which was deleted. So let's look at the implementation of our delete function real quick. So look at singly and delete start. So we're not returning anything, which makes it a bit difficult for us uh, to return our type. So we can update our singly delete function. And the way to do that would simply be just getting deleted here, which would be l.head.value. Now that we have it, we can return the deleted value, and we need to have that in the function declaration, or else we just return -1 if there's no if the linked list is empty. And to keep it consistent, we can also implement it for the delete end. In this case, we're deleting, let's see, so we'll need to have a deleted integer, and deleted would be assigned l.head.value in both of these cases. And at the end, once we have deleted it, we just return it, or we just return a -1. Makes sense? Awesome. So now we can use these functions to, uh, I think our functions might have messed up. Oh no, they haven't, because we have only modified the return type, not the argument type. So now we can use whatever was returned here. We can call it pop, and we just return pop. And now we'll need to do the same thing with peak. To do this, we need to go back and understand the way we are popping items from our linked list, from our stack, I mean. So we are doing delete start. And the way we've implemented that is we are just deleting the head node. Whatever we have at the head, we are setting our head to the current head's next node. So to get the value of our head, we'll need to make our head node public by doing that. So I'm just going to replace all of the instances of our head with a capital H. Did that search and replace. Now we can easily get our s.data.head.value. We can return that, but now we'll need to make our value public. So now that we've made our value public, we can directly uh, access it and return it back. So that's how we would implement uh, our linked list stack. Now, to print it, we've already got a print method in our linked list. So this is why I've been telling you guys to go back and watch the linked list implementation video because it was pretty cool. So we can do something like this where we set the data to a new linked list, a new singly linked list, and where we pass in nil. So it's a completely empty linked list. And now also I forgot to do the stack underflow. So we'll do that the same way we did our overflow where we get the data, we get the lengths. If it is zero, then we just return and we say that uh, there was an underflow and we return a negative one. I'm just going to remove all of these operations and instead, uh, what was our max length earlier? It was 4, I think. And I'm going to implement all the pushing and popping manually. So push link, we would do 1, 2, 3, 4. Again, we can do that. We can do it. We can have our own print for each stack linked. So print stack, which wouldn't return anything, but it would call the data dot print singly. So this makes it a lot more easier. We have essentially created a whole API or uh, a whole wrapper around the singly linked list that we had implemented earlier, and now we have restricted the way the user can interact with our singly linked list. We have created this interface for it. So we can do a print stack here. We can do a print stack again. Let's try to run this. We're still running the vector, so we need to do a stack test stack linked. Okay, so it's a lot more easier to visualize now. You can see that this is our head and we are pushing onto the head. So if we try to push 3 times, then it should be able to push these two elements, but not this one. Let's just make this value a little different. Oops, 3, 4, 5, 6. Now we run. Yep. So we're able to push two of the items, but not the third item, which is what we wanted. Uh, Now we can test our pop method uh, and we can do our push. Okay, we're able to pop and let's see if we're able to pick items from it. Pick linked list. And whatever we got back, we store it in a variable, we print that, and we can also do the same thing with the pop. Awesome. So let's look at this. We picked that 2, 3, 5, 4, 5. We got that back. Let's make the length of our linked list a little larger and add a few more variables to it so it's easier to like visualize what's going on. Let's do that. Do a go run. So we inserted that, we inserted this element, then this. We reached the Stack Overflow, and we did not modify our linked list. Now we tried to peek, we peaked that value, and we still have uh, the same stack. And we popped from it, we popped this element, and now the state of our linked list is this. Let's try to pop a bunch more times until we reach an underflow. So now when we try to run our linked list, we see that we add our elements one by one, and when then we reach a stack overflow, we don't increment anything. We peak, we pop a bunch of times until our list is empty, and we just print out that the stack was underflown, and we return a negative one there. Makes sense. So we in this video we have implemented uh, a stack using a vector and a stack using a linked list. So it would be a vector-based stack and a linked list-based stack. I hope you learned something from it. Uh, in the next video, we will be moving on to implementing a queue using vectors and linked lists. I hope to see you there. Thanks for watching.